Hello students, welcome to the classroom point. So in today's session we shall discuss the chemical bond part 2. So here one question is there, the hybridization and geometry of boron trifluoride molecule is. So let's try to calculate the hybridization first. Boron trifluoride molecule. So hybridization formula H equals to half into V plus M minus C plus A. So here this V stands for the valency of the central atom. Valency of central atom. M stands for the number of monovalent atoms. Monovalent atoms means the atoms which forms only single bond, not double bond, triple bond. C stands for the positive charge. A stands for the negative charge. Actually this is cation, A means anion. So here let's calculate the hybridization of this molecule. So in which V is the valency of the central atom. Here the central atom is the bromine. So bromine is the 17th group element, valence is 7. So 7 plus each fluorine atom forms only 3 bonds. So each fluorine atom forms only single bond. Like that 3 fluorine atoms, they form the 3 bonds. No positive charge, no negative charge. So 7 plus 3, 10 divided by 2 is equals to 5. Means 5 hybrid orbitals are present in this bromine atom. What are those 5 hybrid orbitals? We have to start always with S. So 1 s orbital, remaining 3 p orbitals. So total it is 3 plus 1, 4 orbitals, and 1 more orbital means after p we will get the d orbital. So 5 hybrid orbitals are there. Now the geometry of a molecule not only depends on the number of single bonds but also depends on the number of lone pair of electrons. So now let's calculate the number of lone pair of electrons. Number of lone pair of electrons and hybridization calculation almost same, but a small difference is there. The formula is almost nearly same, a small difference is there, that is half into valency minus total number of bonds minus C plus A. C, A meaning is again same, V also valency of the central atom. Here we calculate the total number of the bonds, that we have to subtract the value. Here in this case we have to calculate if 2 bonds are there. For example, oxygen generally forms 2 bonds. So both the bonds, sigma bond and pi bond, whatever the type of the bond it may be, we have to calculate it. We have to consider it. So valency of the bromine is 7 minus it forms, each fluorine forms 1 bond, so that 3 fluorines minus 3, no positive charge, no negative charge, so that we get the, this is 7 minus 3 is equals to 4 divided by 2 equals to 2. So here 2 lone pair of electrons are there. So out of 5 hybrid orbitals, 2 hybrid orbitals are occupied by now lone pair of electrons. Means only 3 hybrid orbitals are left behind. So that 3 hybrid orbitals of the bromine, they overlap with the p orbital of the fluorine, so that they form the structure like this. Actually, whenever sp3 hybridization is there, then the shape of the molecule is trigonal bipyramidal. The shape of the molecule looks like this. Okay. So this is a trigonal bipyramidal. In this, these 2 positions are occupied by the fluorines. Here 1 fluorine comes, here 1 fluorine comes, because these will be apart from almost 180 degrees to each other. And here 1 fluorine comes, and lone pair of electrons occupy these positions. So now the shape looks like that T shape. You can write the shape of this molecule like fluorine, fluorine and fluorine. Just rotate this molecule so it looks like this. So shape of the molecule is T shape and hybridization is sp3d hybridization. Hence option A is correct. In this particular case, some of the people even they may get the doubt regarding the position of the lone pair of electrons. Why the lone pair of electrons do not occupy these positions? Why they are occupying only these positions? So if you see the trigonal bipyramidal shape, you just see it looks like this. Just you put one atom here, like if you take bromine. So these, whatever these positions are there, these positions and bromine all will be in the same plane, and one is above the plane, one is below the plane. So it is called trigonal bipyramidal shape. In this case, the distance between any two bonds that are present in the plane is equals to almost 120 degrees. And here the angle between the pyramid and the plane is 90 degrees. Okay. So we know that lone pair of electrons occupy more space than the bond pair of electrons. Why? Because the lone pair of electrons are attracted to only one nucleus. But in the case of the bond pair of electrons are attracted to the two nuclei because two atoms are present in the bond formation. Hence, they are attracted to the both of these nuclei. So, the size or the volume occupied by those lone pair of electrons will be less in comparison to the lone pair of electrons. Since lone pair of electrons are occupying the more space, if you keep the lone pair of electrons in the 90 degrees bond angle, so repulsion may arise. Because of this repulsion, the molecule becomes unstable. So that is the reason why lone pair of electrons occupy these equatorial positions, means these planar positions where the distance will be more, so that which will stabilize the molecule. Now let's try to solve the question number 2. In which of the following central atom has different hybridization than others? So let's try to see the hybridization of this central atom of each and every option. So first option is Cl2O. Here hybridization formula is same. I will write here hybridization equals to half into V plus M minus C plus A. Here you no need to calculate the lone pair of electrons. Why? Because they are not asking about the geometry, they are just asking about the hybridization. So here central atom is oxygen. So just let's try to calculate the hybridization. H equals to half into oxygen valence is 6 plus chlorine forms single bond with the oxygen, so that two chlorines, two single bonds, and no positive charge, no negative charge. So the total value is equals to 8 by 2 equals to 4. That means 4 hybrid orbitals, that is 1 s orbital, 3 p orbitals, totally 4. And option B, OF2. Here also fluorine forms single bond with oxygen, so 2 fluorine atoms are there. So similarly, you will get again the same concept. Here also you will get the sp3 hybridization. And C, H2O. Here also oxygen is the central atom and hydrogen forms only single bond. So the 2 hydrogens means 2 bonds. Again you will get the same pattern, that is sp3 hybridization. And option D, if you see SO2 molecule. So in SO2 molecule, each oxygen forms 2 bonds with the sulfur. So that now we need to calculate the hybridization. H equals to half into valency of the sulfur is 6 plus, here these are now oxygen atoms are not forming the single bond, they are forming the double bonds. So whenever double bond is formed, do not count the only one bond in the double bond. We have to neglect all these. So that 6 plus only, so 6 we have to close it, because no positive charge, no negative charge, no single bond, only double bonds are there. So some people may consider the one bond in the double bond, each of these double bond, you should not do like that. So it is equals to 6 by 2 equals to now 3. 3 means 3 hybrid orbitals, that is 1 s orbital, remaining 2 are p orbitals, so that sp2 hybridization. So that has a different hybridization than others is SO2. So option D is correct. Now let's try to solve the question number 3. In following hydrocarbons, which one has 75% P character, 25% S character? Means out of 100%, 1/4 is S character and 3/4 is P character. That is 25% and 75%. Means there are 4 orbitals, hybrid orbitals. In that, one is S orbital, remaining 3 are P orbitals. That means they are asking about the sp3 hybridization. So now let's try to see these molecules. So first of all, this A option is there. C2H4 is there. Means there are 2 carbon atoms to which 4 hydrogen atoms are there. So if you keep like this, there must be a double bond. A double bonded carbon atom always forms hybridization is sp2. Whenever a carbon forms triple bond or 2 double bonds, both this side. So such type of the carbon hybridization is always sp. If any carbon forms only single bonds, no pi bond or no double bond, so such type of the carbon hybridization is always equals to sp3. So now let us see here, both of these carbons are connected by the double bond, so that for both of these carbons hybridization is sp2. Now let us take C2H2. C2H2 is an acetylene molecule. So there is a triple bond. So that here sp hybridization and this carbon also undergoes sp hybridization. Now let us see the CH4 option C, in which carbon is connected to the 4 hydrogens. We know that hydrogen forms only a single bond. So that here carbon hybridization is sp3. So option C is correct. Now let's try to see even option D also. You should not get doubt because they just mentioned the CH2. So we have no idea about the remaining. Actually carbon valence is 4. So it has to form the 4 bonds. So but here only 2 bonds are there. So if you see the carbon atomic number and electronic configuration, 1s2, 2s2, 2p2. So 2 s electrons and 2 p electrons are there. 4 electrons do not participate in the bond formation. Carbon never forms its chemical bonds in its first ground state. It always forms bond formation only in the excited state, in its first excited state. So that one of the s orbital electron jumps into the p orbital and making the excited state electronic configuration of the carbon as 1s2, 2s1, 2p3. So now carbon is having the 4 valence electrons. So with the help of these 4 valence electrons, carbon is able to develop the 4 bonds. So out of these 4 valence electrons, these valence electrons participated in the bond formation with the hydrogen. Just imagine, still 2 unpaired electrons are left behind, not the pair. So 2 unpaired electrons are present here. Now let's try to calculate the hybridization of the carbon here, just using our regular formula. So hybridization equals to half into valency of the carbon is 4 plus 2 monovalent atoms, hydrogen atoms are there. So 4 plus 2 equals to 6 by 2 equals to 3. That means again sp2 hybridization. So the molecule that follows this particular percentage pattern is CH4. Now let's try to solve the question number 4. So in question number 4, which of the following statement is incorrect? They are asking. Non-bonding pairs occupy more space than the bonding pairs of electrons, that just now we discussed. Bonding orbitals in a trigonal bipyramidal molecule are described as sp3d hybridization. So that also just we calculated. And option C, SnCl2 has linear shape. So let us see SnCl2 molecule. Tin is a 14th group element and valency is equals to 4. So just calculate the hybridization. Half into valency is 4 plus 2 bonds, so that 4 plus 2 equals to 6 by 2, that equals to 3. So that we may expect that sp2 hybridization. Now the question is, it is having the 4 valence electrons. Now calculate the lone pair of electrons. Lone pair of electrons equals to formula half into valence is 4 minus total number of bonds equals to 2. So that equals to 2 by 2 equals to 1. So one lone pair of electron is there. So whenever the one lone pair of electron is there, that molecule generally will not give the linear shape with this type of the hybridization. So SnCl2 is an incorrect statement having the linear shape. Actual SnCl2 is having the shape like this, and one lone pair of electron occupy this space. This is a 3 hybrid orbitals. In that 2 positions are occupied by the chlorine atoms and 1 position is occupied by the lone pair of electron. And fifth question is, shape of ammonia is very similar to. See, first of all we must see NH3 hybridization. H equals to half into valency of the nitrogen is 5, it is the 15th group element, plus 3 hydrogens are there, so that 8 by 2 is equals to, I'll write down the value 4. So that means sp3 hybridization, and immediately you calculate the lone pair of electrons also. So half into valency 5 minus total bonds 3. So that equals to 5 minus 3 equals to 2 by 2 is equals to 1. So here one lone pair of electron is there. So in this ammonia molecule, out of actually in 3 hydrogen atoms are there, means 3 bond pairs plus 1 lone pair. So the molecules that are having the same 3 bond pairs and 1 lone pair will have the similar structure to the ammonia. Now we need to see all these options. A CH4, just now we calculated in the above question here. So it is not having any lone pair of electrons, all are the hybrid orbitals, so that it will not follow the same shape. And B option, if you see CH3 minus, so in CH3 minus, hybridization equals to half into valency of the carbon is 4 plus 3 hydrogen atoms are there, minus no positive charge plus 1 negative charge is there. So now it is equals to 4 plus 3, 7 plus 1, 8 by 2 means 4. That means it follows sp3 hybridization. Now let us calculate the lone pair of electrons. That is half into valency of the carbon is 4 minus total number of bonds 3 minus no positive charge plus 1 negative charge is there. So that it is equals to 4 minus 3, 1. So 1 plus 1, 2. So 2 by 2 is equals to 1 lone pair of electrons. So this pattern and this pattern is same, means they will have the same structure. So option B is correct. Let us solve the question number 6. Which of the following has a pyramidal shape? So to show pyramidal shape, a molecule must have the sp3 hybridization plus 1 lone pair of electron. Then that will show the pyramidal structure. Now let us take the option A, XeO3. Just let us calculate the hybridization of xenon here. H equals to half into valency of xenon is, it belongs to the 18th group. So valence is 8 plus no single bonds, single bonds are present, so that we no need to consider remaining, just neglect it. So that 8 by 2 is equals to 4. So that sp3 hybridization. And just you see the lone pair of electrons, half into valency is 8 minus each oxygen forms 2 bonds, like that 3 oxygen atoms are, so they form the 6 bonds. 8 minus 6, that equals to, this is 2 by 2 is equals to 1 lone pair. So this molecule is having the sp3 hybridization with 1 lone pair of electrons, so it will have the pyramidal structure XeO3. Let us see the other option. Just I will give this only shape and you find out the hybridization. So XeF4 molecule square planar. Option C, XeF2. So this molecule will have the linear structure. Option D, XeF6. So it will have the pentagonal pyramidal structure. Let's solve the question number 7 now. The correct order regarding the electronegativity of hybrid orbitals of carbon is: electronegativity of the orbitals depends on the percentage of s character. So that I'll write here, electronegativity of hybrid orbitals is directly proportional to the percentage of s character. So whenever the s character increases, the electronegativity of the hybrid orbitals also increases. So here they had given the three type of orbitals: sp, sp2, sp3. Here how many orbitals are there? Only two, one s orbital, one p orbital. So let us take two orbital contributes 100%. There are two orbitals, so divide the 100 by 2. So each orbital contribution is 50%. So s orbital 50% as well as that p orbital also 50%. And here three orbitals are there, two p orbitals, one s orbital. Imagine they are again contributing 100% towards the hybridization, so that 100 by 3. So s orbital will get the 33.33%, whereas p orbital get the 66.67%. And in this case, 100 divided by 3 plus 1, 4 orbitals are there. So s orbital get the 25% and p orbital, each orbital get the 25%. Like that 3 p orbitals are there. So 3 into 25 equals to 75%. Here also each orbital get 33.33. So for s orbital only one is there, and that's why 33.33%. But 2 p orbitals are there. So 2 into this value, you will get the 66.67%. So in which case s orbital percentage is more here, next here, next here. So that the electronegativity order is also like this. And in the answer, in the options, if you see, sp is more than sp2 is more than sp3. So option D is correct. Let's solve the question number 8. Which of the following bonds is most polar? So directly I am saying the answer, option C. This question has been discussed in the part A of chemical bond DPP series. Earlier to this video, you just follow that, you will get the answer. Everything was discussed there. Now question number 9. Which of the following does not exist on the basis of molecular orbital theory? So it is simple that bond order, we need to calculate the bond order to know whether a particular species exists or not. Bond order means number of bonding electrons minus number of anti-bonding electrons divided by 2. If bond order is equals to 0, that species or molecule does not exist. If bond order is something value is there, it may be 0.5, any value, so there is a chance for that particular species to exist. Initially, I will take the option A, that is H2 plus. We know that hydrogen, each hydrogen will have the single electron. Two hydrogens means two electrons are there. From that two electrons, we have to remove one electron because plus is there. So that this H2 plus is having only single electron. That single electron, according to the molecular orbital theory, enters into the sigma 1s1. So that now bond order is equals to number of bonding electron is only 1 minus no anti-bonding electrons, so divide by 2 equals to 0.5. So there is a chance for this H2 plus to exist. And B, He2 plus. So in this particular case, helium means 2 electrons, 2 helium means 4 electrons, 4 minus 1 electron, so 3 electrons. They are sigma 1s2, sigma star 1s1. So now bond order is equals to bonding electrons, star orbitals are anti-bonding electrons, non-star orbitals are bonding electrons. So here two bonding electrons are there, anti-bonding electron is 1, divided by 2. So 2 minus 1 means 1, 1 by 2 equals to again 0.5. So there is a chance for He2 plus to exist. Then option C, He2, helium molecule. Now 4 electrons are present. So sigma 1s2, sigma star 1s2, bond order is equals to bonding electrons 2 are there, anti-bonding electrons also 2 are there. So 2 minus 2 by 2 equals to 0. So that this molecule does not exist. Even if you take the lithium, Li2. So here 6 electrons, each lithium 3 electrons. So sigma 1s2, sigma star 1s2, sigma 2s2. So totally 6 electrons, and bond order equals to, bonding electrons means here 2 plus here 2, 4, minus anti-bonding electrons 2 are there. So divide by 2. So it is equals to 2 by 2 means equals to 1. So Li2 molecule also can exist. So the one that does not exist is He2. Option C is correct. Let's solve the question number 10. The dipole moment of ammonia molecule is 1.48 d by units. The length of the dipole is, first of all, we must know the formula of the dipole moment. Mu equals to Q into d, where Q is the quantity of the charge, generally electronic charge, d means distance. That is the length of the dipole. So here we need to calculate the d value. So d equals to mu by Q. Q value is always in the coulombs, but here mu value is in the debye units. So the debye units are to be converted into the coulomb meter. So 1 debye unit is equals to 1 d is equals to, we can write it as a 3.33 into 10 power minus 30 coulomb meter. So that now I will take the mu value, that is 1.48 into 3.33 into 10 power minus 30 coulomb meter divided by, here length of the dipole, so Q value we have to take, that is 1.6022 into 10 power minus 19 coulombs. Coulombs get cancels out. So we will get the length in the meters. So the value is approximately is equals to 3.08 into 10 power minus 11 meters. So this, if you convert into the nanometers, so that shall be equals to 0.0308 nanometers. So here anyhow we got this one. So option A is correct. Now let's try to solve the question number 11. Which one of the following does not have the intermolecular hydrogen bonding? Here they forgot to put, this is actually methyl alcohol. So now let's try to see all these molecules. H2O forms the intermolecular hydrogen bond, H2O, HF and methyl alcohol. But orthonitrophenol do not form. I will take the structure of orthonitrophenol. So in the case of the orthonitrophenol, the hydrogen bond is formed between the hydrogen and oxygen of the molecule within the molecule. So this hydrogen bond we call it as a intramolecular hydrogen bond. So in this molecule, intramolecular hydrogen bond exists, not the intermolecular hydrogen bond. Hence option B is correct. Now let us see question number 12. Arrange in increasing order of the boiling point values. Generally boiling point value increases by increasing the van der Waals forces. When size of the atom increases, boiling point increases. So boiling point is directly proportional to the size of the atom. Why? Because when size of the atom increases, van der Waals forces also increases. So in this case, hydrogen is the common thing in all these hydrogen halides. So fluorine, chlorine, bromine, iodine. So if you take the molecules, the size increases like this. So that's why actually we expect that hydroiodic acid should have the highest boiling point. But among all these hydrogen halides, HF forms the hydrogen bond. So due to the formation of the intramolecular hydrogen bond, HF abnormally shows the highest boiling point than all these remaining hydrogen halides. So that is the reason why HCl is having the least boiling point than the HBr, then hydroiodic acid, and the highest boiling point is with the hydrofluoric acid. So this is the order which we need to finalize out. So option A is correct. Let us solve the question number 13. So in this 13, they are asking the hybridization of carbon atoms in carbon-carbon single bond is. So they are asking, let us try to write down the given molecule H. Molecule begin from here, H connected to the carbon, next triple bond, next single bond carbon, double bond CH2. So I have just discussed in the previous question, one of the previous question, that whenever the carbon forms triple bond, the hybridization is sp. Here also hybridization is sp. Here carbon forms double bond this side. You should not see this side double bond is there. So it is sp2, and here also sp2. So they are asking the hybridization of the carbons that are connected by single bond. So their hybridization are respectively sp and sp2. So option C is correct. Now let us see the question number 14. Carbon-carbon bond in C2H6 undergoes heterolytic fission. The hybridization of carbon atoms is. So just you take, this is the CH3 and the CH3, they said C2H6. So heterolytic fission means the bonded electrons completely will be shifted to the one of the bonded atom. Means unequal cleavage of the bond is called the heterolytic cleavage, because a bond will have the two electrons. In the two electrons completely will be shifted to only one side, maybe this side or that side. So that shift is called the heterolytic cleavage. And if you take a bond like this, for example, now homolytic cleavage means equal cleavage of the bond. So one electron goes to the one of the bonded atom, the other electron goes to the another bonded atom. But in the heterolytic cleavage, both of the bond electrons will be shifted completely to the one of the bonded atom. So since this particular carbon is losing all electrons to this CH3, this CH3 becomes CH3 minus. Since it is losing the electrons, it becomes CH3 plus. So carbocation, whenever carbon is with the positive charge, its hybridization is sp2. In the negative charge, its hybridization is sp3. So sp2 and sp3 hybridization, hence option C is correct. Let's see the 15th question. The enolic form of acetone contains sigma bonds, they are representing as A, pi bonds as B, and lone pair of electrons as C. So first of all, let's write down the acetone structure. This is acetone. Means actually here also we can write this CH3, but in tautomerism we need to shift one of this hydrogen. So these electrons will be shifted between the carbon and this carbon, and these pi bond electrons will be shifted over to the oxygen, and this hydrogen will be shifted over to the oxygen atom, and finally we get the carbon double bond, here oxygen and hydrogen, and here two hydrogen atoms are there. So I'll write those hydrogen atoms separately like this, and here three hydrogen atoms are there. So I'll write those hydrogen atoms also separately in order to calculate the number of sigma bonds, pi bonds very easily. So sigma bonds, let's try to calculate, which are actually defined as A. Now let's try to calculate the sigma bonds. 1, 2. In double bond, one is sigma bond, one is pi bond. This is sigma, this is pi. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds are there. And pi bond, how many are there? Only one is there. And lone pair of electrons means oxygen will have the two lone pair of electrons every time. So lone pair of electrons are equals to 2. So 9A, 1B, 2C. Option A is correct. Now let's try to calculate the bond order of N2 minus anion is. N2 minus means total number of electrons are, nitrogen means 7 plus 7, 14 plus 1 extra electron is there. So totally 15 electrons are there. So according to the molecular orbital electronic configuration, we can write sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Totally 4 into 2, 8 electrons are over. So here pi 2px2, pi 2py2 and sigma 2pz2. So totally 1, 2, 3, 4, 5, 6, 7 into 2, 14 electrons over. So one more electron is left behind, that is pi star 2p x1 equals to pi star 2p y0. Since these are having the equal energy, so that I am just representing this one, though electron is not there. Now let's try to calculate the bond order. Bond order means number of bonding electrons minus number of anti-bonding electrons divided by 2. Number of bonding electrons means without star. We have to calculate the number of electrons in the orbitals without star. So here 2, 4, 6, 8, 10 electrons are there. 10 minus with bond with star. Here 2, 4 plus 1, 5. So 10 minus 5 by 2, that equals to, so here it is 5 by 2, that means 2 and half, 2.5. So the bond order in N2 minus anion is 2.5. Hence option C is correct. Let us solve the question number 17, which is very good question and important question also. Which of the following has the maximum bond strength? Bond strength is directly proportional to the bond order. When bond order increases, bond strength also increases. First of all, let's calculate the bond order for oxygen molecule O2, which is having the 16 electrons together. So it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x2, that equals to pi 2p y2. Next, pi star 2p x1 equals to pi star 2p y1. Now calculate the bond order. Bond order equals to, as I said just now, number of bonding electrons minus number of anti-bond electrons divided by 2. So here bonding electrons 2, 4, 6, 8, 10 minus anti-bonding electrons 2, 4, 4 plus 2, 6 divided by 2 equals to, this is 4 by 2, that equals to 2. So there is a double bond between the two oxygen atoms in the O2 molecule. Now let us see the B, that is O2 plus. O2 plus means separately no need to write down. O2 lost one electron, that's why O2 plus has come, means you remove this electron. So when you are removing this electron, you have to remove the one of the anti-bonding electron. So directly bond order becomes now 10 minus 5 by 2, that equals to 2.5. C, O2 minus. O2 minus means you add one more electron to these anti-bonding electrons. So 6 becomes 7 now. So bond order is equals to 10 minus 7 divided by 2, that equals to, so it is 3 by 2 means 1.5. And option D is O2 minus 2. Means you need to add one more electron, means total 2 electrons to these anti-bonding electrons. So bond order is equals to 10 minus 8 divided by 2 is equals to 2 by 2 means that is equals to 1.0. So bond order, I will take another color. Bond order is more for the O2 plus, then O2, then O2 minus, then O2 minus 2. So this is the correct order. So maximum bond strength is with the O2 plus. Option B is correct. Question number 18. So this question already just in previous questions only discussed. So just I am giving the direct answer, that is option D. Now let us see the question number 19. I will move this page upward. So once again I will write down here question number 19. The molecular orbital configuration of a diatomic molecule is given. This is the molecular orbital. Just they are asking the bond order. So it is very simple, that number of bonding electrons minus number of anti-bonding electrons divided by 2. So bonding electrons, how many are there? 2. This here 2 are there. 2 plus 2 4. 4 plus 2 6. 6 plus 4 10. Minus anti-bonding electrons 2 plus 2 4 are there. So 10 minus 4 by 2, 6 by 2 is equals to 3. So 19th question, option A is correct. Now let us solve the question number 20, which is not true according to the valence bond theory. So a covalent bond is found by overlapping of orbitals with unpaired electrons with opposite spins. This is correct statement. These are just statements only, which is in the postulates of the valence bond theory. A covalent bond is found by the overlapping of orbitals with unpaired electrons with the same spin. Same spin is not correct, opposite spin is correct. So incorrect statement is option B. So for 20th question, option B is correct. So dear students, hope you like this video. If you like, please share and comment what type of the concepts and content you want. Thank you.